Alex Gorodetsky, who will continue in the similar vein to what Ben Beiersdorfer just talked about, and tell us about sampling algorithms for generalized model ensembles in a multi-fidelity uncertainty quantification framework. Please fire away, Alex.
All right. Thank you, Rob, and thanks a lot for still hosting this in these times. So I will be talking about again, as Rob said, generalized model ensembles and sampling algorithms. And this work is done jointly with Gianluca Gerasi, Mike Eldred, and John Jakeman. I believe John Jakeman's also on the line. All three of them are at Sandia National Laboratories. So when we're talking about generalized model ensembles here, I'm just talking about multiple models in a very holistic sense. So the observation is that when you're going to create or analyze a system, many models and simulations are used. You never go to the final high fidelity result, especially when you're trying to analyze or eventually model, make decisions about complex systems. And usually these intermediate models serve to develop the eventual high fidelity model. And there's a wide, and they can be very heterogeneous. They could be the same physics, they could be different physics, which I'll go into in a second. The goal of here, when I'm talking about generalized model ensembles, is how do we use all the pieces of information source that went into developing some complex simulation, also for the purposes of analysis, and in particular for uncertainty quantification. And so the types of information sources that we can consider are very wide-ranging. So for instance, there could be a hierarchy of fidelity. So here, as an example, in fluids, there could be simplified physics ranging from potential flow to RANS, all the way to LES, and then to DNS. So these are hierarchy of fidelities for a single particular simulation. But even within fidelities, there might be ensembles of peer models. So for instance, it might not be clear which RANS, which turbulence model should you use, or there might be competing methods. How do you use them together? And furthermore, even within each of these peer models, there might be discretization levels or solver parameters that you might be able to choose in order to develop the simulation. And finally, we can view information sources more broadly. They can include, for instance, experimental data or surrogate models, reduced order models, and so on and so forth. So I guess I'll view this. I was asked, or the presenters were asked, to look at some high-level questions, and I don't have the answer to all these questions. But in general, these are the types of things that my perspective on these problems that I'm looking to answer. The first is, how do we model actually the multifidelity uncertainty quantification problem? But more specifically, how do we take what I just described as information sources, and how do we in algorithms actually encode these as how do we represent these relationships? As an example, we might have discretizations of hierarchies, physics hierarchies, competing peers, as I said. How are these actually encoded in our algorithms? Oftentimes, for instance, discretization hierarchies are encoded as discrepancies. Physics hierarchies are sometimes encoded through control variates, which is what I'll talk about now. That requires statistical correlations. There might be other ways to encode these representations, and then these other ways will yield different algorithms. However, it's not clear, is there a best way of practice of translating what we know about the multi-fidelity information sources into an encoding of their relationships? It's taking a while to show up. And then tied in with that are algorithmic objectives of multifidelity uncertainty quantification. So we've already seen some of them. They could include variance reduction. They could include bias reduction. They could combine them all into mean squared error reduction. So this from the frequentist point of view. Or you can do, for instance, probabilistic predictions, where you consider general fusion of the models to try and get credible intervals on their predictions. So how do we model them together how do we model the whole problem together to obtain these objectives? And I'm very interested in, but don't have the answer to, are there any general approaches? It seems like there are many specific approaches for specific situations. However, are there general approaches by which many existing algorithms can then be viewed as specific cases? And would this allow us to kind of think of generalized theories for multi-fidelity uncertainty quantification? So those were the modeling questions. There's also quite a few algorithmic challenges even within a particular case. So one challenge that we encounter is often there's a database of evaluations, for instance, legacy data that was obtained on some supercomputer to which you don't have access to. How do we use these evaluations without being able to query the model further? Another problem is that data has noise, and noise, I use this very loosely. It could mean actually corrupted evaluations, but it could also mean, for instance, numerical noise that comes from unconverged grids. And this happens because when you develop simulations, you often tune the solvers to fixed parameter settings. You can't explore all of the parameters, all of the uncertainty. And so the simulations may not be as converged as you think in that whole domain. There could be problem geometries that lead to meshing issues. This is really studied quite a bit and is an interesting topic. Then there's also nonlinearities and time-dependent problems. So I'm interested in applying these to fast nonlinear systems that could even be chaotic systems. And a lot of the approaches, for instance, based on correlations, are maybe no longer applicable in these highly nonlinear situations. So, and finally, there might be that, and is often the case, where simulation models have different inputs. So this is extremely common when you, for instance, talk about physics hierarchies, where every level of the hierarchy replaces physics with models. For instance, think closure models. Now, since not every higher level of the hierarchy have these models, each information source has their own set of uncertain model parameters, but then all of them also share another set of uncertain model parameters. So these could be, for instance, environmental parameters or boundary conditions. Now, in this talk, I'll focus this a bit more on sampling algorithms. And the idea is to develop sampling algorithms to avoid explicit or implicit orderings based on either model fidelity or correlations. And the reason why I focus on correlation is because this talk is specifically focused on variance reduction. So variance reduction of Monte Carlo type estimators. And the point of view that we take is an optimality and convergence point of view. So I just want to answer the asymptotic question of what is the best possible variance reduction that you can achieve if you had unlimited information from your low fidelity information source. A dual viewpoint is if your low fidelity information source becomes exponentially cheaper, so orders of magnitude cheaper compared to the high fidelity source, what is the best possible variance reduction that we can achieve? Coming up a little bit slowly for me. So now it just came up. So I'll go ahead and show that some existing approaches that rely on recursivity within their sampling strategies can be limited from this perspective, because they can. There could be situations where you can evaluate the low fidelity model in infinitely more time, but because how you're allocating the sampling, you cannot gain any further variance reduction when one does exist theoretically. And this is due to orderings, either again because the situations are hierarchical or your algorithm has ordered them in some way. So for the rest of the talk, I'll first introduce the notation. So this will be about notation will be on Monte Carlo and control variates, which will be the main tool that I investigate. Then I'll talk about recursive difference estimators, which are used within bias and variance MSE schemes like MLMC, and nested difference estimators, which create MFMC, multi-fidelity Monte Carlo. I'll talk about some convergent approximate control variates, and then some higher level directions that we're pursuing for general probabilistic models of the multi-fidelity UQ problem. So let me begin with Monte Carlo. The idea here, just to set notation, is we have a Monte Carlo estimator where Z is the input of parameters and they're uncertain. And so we want to get an estimation of the expectation, which is a weighted sum. This estimator is unbiased in the sense that the weighted sum has the same expectation as the quantity of interest that we're seeking, and the variance decay is like 1 over n. So 1 over n, this is the factor, this is the term, this variance is the term that we want to reduce. So the way that we're going to do this is we're going to concentrate on a control variate scheme. So this is one model for multifidelity uncertainty quantification from the point of view of some of my of the questions that I asked before. And so the idea is, and Benjamin talked about it earlier, is that you introduce a correlated information source. And I highlight this because the only thing that matters in control variates is correlations. It doesn't matter at all anything else about the problem. It doesn't even matter if it's from the same domain of the problem. If the source has the same inputs and has the same correlation, it can be used effectively. So suppose we know the mean of this source. Okay, so in the control variate setting, which was probably before 1981, but at least the earliest paper I know that named it control variates was 1981, is you know the low fidelity information source statistics, for instance, the mean, and you form a weighted sum to compute a new estimator, which is a combination of the Monte Carlo estimator and a weighted discrepancy between the Monte Carlo estimator of the new information source and its mean. Now, if you choose the weight carefully, you can achieve an optimal variance reduction that corresponds to the correlation, as I talked about earlier. And the way to think about it is if the correlation is 1, that means that the low fidelity source is essentially telling you everything you might need to know about the high fidelity source, and you get 0 variance of the estimator. If it's uncorrelated, you get no reduction, and you just maintain the Monte Carlo. Monte Carlo estimator properties. So the key point here is correlation in control variance. So how do we do this for multiple models? For multiple models, can you see the slides? There's a question that it was.
I can see them. Maybe it was just loading. Maybe it was just loading. Elizabeth, is it visible now?
Yes. Elizabeth, yeah, I think it is. Yeah, it loads a little bit slowly.
Perfect. Okay, yeah, there's a little bit of delay, and I think Alex is experiencing it as well because he's controlling it remotely.
Yeah. Okay, so now when we consider multiple models, multiple information sources, we can introduce each of them with its own weighted sum. So this is, again, another ansatz for multifidelity uncertainty quantification. And then, again, we have to, these weighted sums have to have known statistics, they have to have known means, and then they each have their own weights. So, so given these weights, we have another variance reduction result that's very similar, where we now replace this rho, which is a correlation between just the one model and the high fidelity information source, with an R squared. And the R squared now, corresponds to the correlation amongst all the models. And so this is the key note. Within this key property, within this modeling framework, what matters is the correlation and the covariance between all the models, not just the low fidelity models and the high fidelity models, or a sequence of low fidelity models in a hierarchy. Here we see the terms that come into play are the covariance between the high fidelity model and all the low fidelity models, which is indicated by the bold Q, all between all of the low fidelity models as well. And the optimal weight is given, again, the optimal weight is a function of all of the correlation amongst all of the estimators. And as you might imagine, the greater the correlation amongst everything, the more variance reduction achieved by the control variate given by this form. All right, so now in uncertainty quantification, we have a slightly different issue where we have low fidelity information sources, but we do not know their statistics. So I'll try and put the whole slide instead of line by line because of the delay. So we want to use this modeling onsets. Again, it's just a model for the multi-fidelity UQ problem, but we don't know mu and we don't know alpha hat. So what we're going to do is we're going to estimate it. And so when we're going to estimate it, we're going to estimate it with additional samples. And so here I want to point out these particular sample sets. They're inputs to the same model, same information source. However, there might be different sets of inputs for the same information source to evaluate the mu term versus the qi term. And it turns out that this general ansatz can be used to analyze some existing estimators that are found in the literature. And this is what I'm going to focus on for the next part of the talk. All right. When there's a particular model, so when m is equal to 1, there's one low fidelity source. This is exactly the approach taken by Pasupathy 2012, by Leo Ng and Kieran Wilcox in 2014. Now, when there's multiple models, there's multiple options for how do you handle this, how do you distribute the evaluations amongst the Q and the mu. And there's two general families that are commonly used in the literature. The first are so-called recursive difference estimators. And so these estimators are used within typical MLMC and multi-index Monte Carlo loops. Again, I'm using the multi-level Monte Carlo and multi-index Monte Carlo to talk about general bias reduction, within which is an estimator called the recursive difference estimator. And then another sampling allocation that we're calling recursive nested estimator leads to the multi-fidelity Monte Carlo algorithm. And we'll show that because of the way that these recursive techniques allocate samples, they tend not to converge to the optimal low fidelity, optimal control variate with the known mean. And since we're using this ansatz as an approximation, convergence to the actual approximate control variate is a very attractive thing that we want to get. So now what I'll do is I'll show a brief interlude of another issue with recursivity, and then I'll get back to this examples. And I show this interlude as a kind of motivation and also brief introduction to notation for the recursive difference estimators. And so this is a stochastic ODE, modeling payoff options. And so this was the example from Giles in 2008, and what we've heard about earlier today. So here Euler-Maruyama is used for the time integration scheme, and then we get a multi-level problem by using different resolutions. And different resolutions are leveraged by rewriting the expectation of the payoff at the finest discretization as a telescoping sum. And the variance then becomes the variance of each of the discrepancies. And so in this particular problem, there's a very nice convergence of the variance of the discrepancies, which are much smaller than the variance of the original model, which leads to significant variance reduction. Okay, so now what I'll do is in this recursive problem, I'm going to change it a little bit, but I'm going to change it by adding noise, just random evaluation, into the third level to simulate corruption. So when I simulate corruption, I can get it at all these different lines correspond to different rates of corruption. So the yellow one, which is hard to see, is 1 out of every 100 sample is corrupted. The orange one is 1 out of every 1,000 is corrupted, and so on and so forth. As more and more corrupted, you see this variance decay becomes broken, and therefore this recursive approach begins to suffer because all of the information is passed through this recursive hierarchy. Okay, so with that, let me dive a little bit deeper into what this recursive difference estimator is actually looking like, and I want to give it from the perspective of the approximate control variate scheme that I was talking about before. So what I'll draw on the right here is a visualization of the sample allocation strategy. And this is the most important part because it distinguishes the different algorithms from each other. And on the left, I'll talk about how you construct a multi-model estimator from a set of from a recursive estimator. So we're going to consider a set of low fidelity information sources, and we're going to use the so-called recursive difference estimator, which creates a new estimator, which is Q minus Q1. Q is like the Monte Carlo estimator, Q of the high fidelity, Q1 is the low fidelity, and mu1 is the known statistics. This is unbiased. This can be viewed as a particular control variate with weight -1. And so we can build it up slowly by saying that suppose we have a two-model case, and here's a two-model case. We don't know mu1, okay? So in order to get mu1, we're going to partition it with additional samples of z1, 2. So again, we evaluate Q with in this pink z samples. We use the same samples for Q1 hat, but then we use additional samples for mu1. But we don't know, we want to then accelerate mu1 because we have higher discretization. So we're now going to replace mu1 with another recursive difference estimator. This recursive difference estimator, the Q2 hat, is going to share the samples with mu1 hat. And then it's going to have more samples for the mu2 hat. Okay. So now we can keep doing this over and over again and eventually build a set, an estimator that has many models and has this type of recursive sampling strategy. And so this is the sampling strategy that's used within multi-level Monte Carlo by building up recursive differences estimators. And you can rearrange it into being essentially, by grouping terms corresponding to the same models, as an approximate control variate with a fixed weight -1 and the variance, which I've talked about earlier. Okay, so now we can do the same thing with a different type of recursive nested estimator that's used with multi-fidelity Monte Carlo. And so here we start with the control variate with two models. And we're going to say, well, we don't know mu1. We don't know mu1. So we're going to estimate mu1 with another control variate. This control variate is going to share the samples for Q1 and then introduce another set of samples with the third model. And so here you see that these control variates become nested, and you can keep doing this until you've exhausted your models. And eventually you have this nested sampling strategy shown here. And then you can group all the terms within this nested again into an approximate control variate representation. Okay, so what is the problem with the recursivity? And the problem is the following. Because of the sample allocation strategy, it actually doesn't, the correlation between all of the models is actually not captured. There are cancellations that are not accounted for. And so what this means is that we get a limited reduction. So the way to a variance reduction, the way to interpret the plot is the following. The Monte Carlo line is a variance reduction ratio of 1 because we're comparing to Monte Carlo. Then we have a couple of black lines. These are optimal control variate 1, 2 models, 3 models, and all models. And when we talk about optimal control variate, we're saying that we know the statistics, we know the mu. And now on the x-axis, you can view this as either the low fidelity models becoming as cheap as possible, or you're increasing the number of evaluations of just the low fidelity models. The number of high fidelity models is constant. So you would hope, because you've used this control variate ansatz for your approximation, that as you have more samples, you would converge to the optimal control variate. But because of the recursive sampling strategy, what you get is a convergence just to the most correlated model. So again, the most correlated model, if you order based on correlation, you will converge just to the most correlated model. And so in the paper, we can formalize these by showing that the R squared of the recursive difference and the recursive nested estimators are essentially bounded by the correlation of the most correlated model. And the important reason is that this particular sampling strategy breaks the correlation between the low fidelity models that is needed in order to guarantee the convergence. Why does it break it? Because really the thing that matters in control variates is the correlation between the estimators that make up the first column of these sampling schemes. Remember, if these first columns are correlated, then the control variate achieves its maximum reduction. By changing the sampling strategies, you essentially decorrelate the first columns, so the Q hats. However, you do so by gaining in more accurate estimations of the mu. So it's a trade-off. Sometimes it's more beneficial to estimate the mu, but sometimes it's beneficial to estimate the Q hat to maintain correlation to get maximum variance reduction. So now I want to show a couple of examples of these types of techniques, of these types of results. So the first example, first I want to show how to decorrelate it. I apologize. So again, we're going to have a convergent estimator, and we're going to work within this modeling ansatz. So again, this modeling ansatz has a Monte Carlo estimator or a general estimator for the high fidelity information source. Then it has two estimators for the low fidelity information source. The first is QI, the second is MUI, and the more correlated QI is to Q, the greater the reduction if mu was known. So as you get more and more information source to get mu accurately, you want to also have QI hat and Q be highly correlated. So this is the estimator ansatz between with which we're modeling the multi-fidelity uncertainty quantification problem. So how do we get a convergence? So to get convergence, what comes up? A bit of a delay. So to get convergence, essentially what we can do, I'll say before it comes up, is we evaluate the low fidelity simulation source QI at the exact same samples that we evaluate the high fidelity simulation source. And then all the rest of the samples go to mu I. Okay, so it's there's many types of ways to do this, but that's the simplest way. You take QI hat, you evaluate at the same exact samples at Q hat, and all of the rest of the samples you use for mu I hat. And the reason why this guarantees convergence in the limit of infinite information source is intuitive in the fact that mu I hat then converges to mu I, the true statistics of the low fidelity information source. And the benefit is that it maintains the correlation amongst all of the required terms to maximally leverage the ansatz, to maximally leverage the control variate representation. So these different simulation models, again, looking at a visual representation of the sampling strategy, what you'll notice is the first column, which again corresponds to QI hat, it only has the same sample allocation strategy as the Q, as the high fidelity model. So if you look at, for instance, this box, this is the high fidelity model. This is the low fidelity model. It's the same as this box. This is the second low fidelity information source. It's the same as this box. And the same thing with this allocation strategy. The thing that differs is now what you do for the mu. So for the mu, we're just adding any additional information samples, information source additional samples to estimating the mu. And now you can see that these samples could come from the same thing that either the recursive difference or the recursive nested estimator is using. We can actually reuse their samples in a more efficient way for some problems. So just to compare this explicitly, for instance, for the MFMC, all we do is ignore the samples that you had in the first column of the low fidelity simulation sources, and just consider the same exact samples for the high fidelity information source. As you get more and more samples for the low fidelity information sources, the shared samples in the upper right will converge to the optimal control variate scheme because it maintains correlation amongst the estimators. So this just shows that as we increase the effort expended on the low fidelity models, we can actually converge to the final, to the optimal variance reduction. And this is, we can prove that this is the case. Please see the paper. And interestingly, we showed that sometimes it is beneficial to accelerate the mu, and sometimes it's beneficial to accelerate the q, which is correlated. So you can make hybrid estimators that some set of the low fidelity information sources are used to accelerate some mu, and the rest of the low fidelity information sources are used to accelerate the high fidelity statistics of Q. And so with this type of technique, we can essentially generate estimators that converge to any target level, and they can have different rates in the beginning. And so you might be able to do a hybrid approach where you select on the fly K and L to get an optimal variance reduction for a given set of effort, for a level set of effort, and that's what we do. I want to skip the next slide on sample allocation, but because I'm running a little bit of time, I want to show some examples. So here's a Viscus-Burger's equation. It just has 6 discretization levels. We have 2 examples. The first shows that if we can sample the high fidelity model more, so it's within our knob that we can tune, then all of these estimators essentially perform the same. However, if the number of high fidelity models is fixed, because for instance they're from legacy evaluations, beyond a certain point we're able to achieve almost an order of magnitude benefit compared to recursive estimation strategies. So again, this is problem dependent on what knobs you can choose. But let's see what happens for the robustness issue. So remember here, I corrupt the 3rd level. So here we consider no corruption. And we're just comparing, we're comparing 3 estimators, the KL estimator, the recursive difference estimator, and a weighted recursive difference estimator with a non-1 weight. With no corruption, we have this variance reduction. They all work similarly. Then we corrupt 1 out of every 100,000 or 10,000. Then 1 out of 10,000. We see that the ACVKL approach, which is not recursive, is able to maintain good variance reduction, while recursive strategies now begin to suffer because, again, the information is only passed across the levels, through the hierarchy, from the least correlated to the most correlated models. Okay, so here's another example on robustness to discretization aggressiveness. So here is a PDE modeling elastic wave propagation. So this is multi-fidelity and multi-level in the following sense. We have this is a nonlinear PDE. We have 2 numerical schemes, which we call the fidelities. The one is a second order scheme. The first is second is a first order scheme. And for each scheme, we have multiple discretizations. And so here we have 2 materials, and we have a wave propagating starting from around here, if you can see my cursor, and then propagating to the right. Our quantity of interest is the properties in this block, in this box. And so here we see the solutions for the first order scheme, the second order scheme, and different discretization levels. So now we compare the estimators for these different cases, and we're going to consider 3 different situations, all of which are common in application. The first is a single fidelity, so single solver, and a discretization hierarchy. So this is the multi-level case. The second is multi-fidelity with discretization hierarchies. And the bottom is multi-fidelity, but instead of having a nice discretization level where we go 200, 100, 50, 20, it's very aggressive. So we could go from 200 to 20 to 10. So we don't have a geometric decay, for instance. In the standard case, what you see is the recursive approaches work very well. So in this case, the multi-fidelity Monte Carlo approach works quite well. Once you consider the multi-fidelity case, now the ACVKL is slightly better, but overall, they're fairly good. All of them are fairly good. And when you consider aggressive coarsening, so this is when, for instance, you don't have super nice discretization level, now we see that there begins a gap to develop between the ACVKL, so the general control variate approach, and then the recursive approaches. The black line is the Monte Carlo variance reduction. The x-axis is the target cost. So in general, you see that it performs well across a variety of situations, even in the standard discretization hierarchy case. All right, so now now a couple of observations to lead into a very brief discussion about on one other topic. The first is that the approximate control variate is a heuristic ansatz. Okay, so we just through intuition developed it because, first of all, we know that the control variate is one way to fusing data together, and the second, these existing very effective techniques can be viewed as an approximate control variate. And indeed, the recursive approaches often work really well, and the general case is not often needed. But again, it has these limitations when you don't have the structure that you want. However, when there is other structure, for instance, either recursivity, when there is structure like recursivity or even pure models, then you do get computational and algorithmic gains from exploiting it. So computational gains might mean that you require less data, or you can prove optimal sampling allocation strategies, and you can do faster inference. So these are the type of computational gains. And then the second observation strategy is many of the techniques require pilot samples. And so, especially in control variates, it's very difficult to analyze what exactly pilot samples, what their effect is on estimating the needed parameters, like the control variate weight and so on and so forth in these heuristic settings. We have some empirical results, but it's difficult to analyze. Do they introduce bias or what do they do? So what would be great is if there's some way to derive new ansatz. So can the ACV, which was derived from intuition, can it be derived from first principles? So I'll show you a brief work that we've done and just submitted, where the answer is yes. We can look at the ACV that way. But more generally, can better and problem-dependent estimator ansatz be obtained? And the answer is probably yes, and we're working on this, but don't have any results to present today. And so the general idea of this way to obtain these settings is that we've worked on is we're going to parameterize a set of model relationships and then use statistical inference ideas instead of a fixed combination, for instance, as a correction, as a control variate correction for the inference. So first principle inference is, for instance, Bayes' rule as a first principle inference. And then we hope that we can incorporate within this structure the modeling relationships. So one way to naturally model these relationships, and I apologize for the poor quality, is through structured models of graphs. So for instance, you can model multi-level things and peer things. You can also model multi-level things in trees. So we've investigated this. I want to finish up here and just show, I'll answer any questions because Rob says I have 3 minutes. The idea is that I have different types of models, for instance, pure low fidelity, pure hierarchy, or pure can be modeled, and different covariance matrices can result, leading to different computational efficiency things that we can exploit. And if we form this in terms of Bayes' rule, which I won't go into here, I'll just go into my conclusion side, we can actually recover the control variate ansatz, the approximate control variate ansatz. Unfortunately, I don't have time to present that. So with that, I'll just put up my conclusion sign and open up for questions.
Thanks a lot. Thanks for a great talk, and for also showing all these links between the approaches, which is exactly what I was hoping for. And also, I do like the last few slides because they're opening up some ideas in the direction of using machine learning ways of learning all these things. So I invite people for the discussions later on. The slides of all the speakers will be available. you can have a look at those slides. So do have a look at Alex's slides.